How does one mechanical failure end everything? That's the question that haunts everyone who's followed the tragic crash that took the lives of NASCAR legend Greg Biffle, former Delta Airlines captain Dennis Dutton, and his son Jack Dutton on a January morning in North Carolina. In modern aviation, aircraft are designed with redundancy built into every critical system precisely so that one mechanical failure doesn't end everything. Twin engines, so one can fail; dual hydraulic systems, so one can leak; multiple electrical generators, so one can quit; backup flight instruments, so primary ones can malfunction. The entire philosophy of aircraft certification is that no single mechanical failure should result in loss of the aircraft or loss of life. So when a modern twin-engine jet does crash after what appears to be a single mechanical failure, we need to ask the hard question: was it really just one failure, or was it one failure that exposed a dozen other vulnerabilities that should never have existed in the first place? Welcome back to the channel. Today we're examining the Greg Biffle citation disaster from first principles, understanding how one mechanical failure cascaded through a system that should have caught it, and why the safeguards that were supposed to prevent tragedy simply weren't there when they were needed most. Let's start with the mechanical failure itself, because understanding what went wrong mechanically is the foundation for understanding everything else. The Cessna citation. Two involved in this accident, registration November 257 Bravo Whiskey, was powered by two Pratt & Whitney JT15D turbofan engines mounted on pylons on the rear fuselage. These engines are proven, reliable power plants with thousands of examples operating worldwide. Each engine produces approximately 2,500 pounds of thrust at takeoff power. Together, they provide more than enough power to lift the aircraft, climb at impressive rates, cruise at high altitudes, and fly long distances efficiently. But jet engines, despite their reliability, are also incredibly complex and operate under extreme conditions that would destroy lesser machines in seconds. Inside the combustion section, fuel is being burned at temperatures exceeding 2,000 degrees Fahrenheit. Turbine blades are rotating at speeds approaching 20,000 revolutions per minute. Compressor stages are compressing incoming air to pressures 10 times atmospheric. Tolerances between rotating and stationary parts are measured in thousandths of an inch. Everything must work in perfect mechanical harmony, perfectly balanced, perfectly timed, perfectly cooled, or the engine will destroy itself. Jet engines are designed to ingest air, and only air. The inlet is shaped to capture and smooth the airflow. Screens and separators remove rain and ice. The entire front end of the engine, the fan section and compressor stages, is optimized for processing smooth, clean air at high velocity. What jet engines absolutely cannot handle is foreign objects, solid objects, things that shouldn't be there. When something solid enters a jet engine at high speed, the results are catastrophic and nearly instantaneous. The fan blades at the front of the engine are the first things that foreign object will strike. These blades, despite being made of titanium alloys or hardened steel, are spinning at tremendous velocity. When they strike a solid object, something with real mass, real density, the kinetic energy involved is enormous. Blades bend, blades crack, blades shatter completely, and when one blade fails, the imbalance it creates often causes adjacent blades to fail as well. Within a fraction of a second, you can go from a perfectly functioning fan section to a completely destroyed one. But the destruction doesn't stop there. Pieces of shattered fan blades become projectiles traveling at hundreds of miles per hour through the engine. Some travel forward, punching through the inlet, cowling, potentially striking the fuselage or wings. Others travel backward into the compressor section, striking compressor blades and destroying them. Metal fragments continue downstream into the combustion section, damaging fuel nozzles and igniters. They pass through into the turbine section, striking the delicate turbine blades that extract energy from the hot exhaust gases. Within seconds, literally within 2 to 3 seconds, a jet engine experiencing catastrophic foreign object ingestion goes from producing maximum thrust to producing zero thrust. RPM drops to zero or near zero, exhaust gas temperature spikes as unburned fuel passes through. Oil pressure drops as pumps lose drive. Fuel flow goes to zero as the fuel control unit senses the loss of RPM, and every warning system associated with that engine activates simultaneously. Master warning lights, master caution lights, engine fire warnings potentially if hot metal has breached containment, are all warnings blaring in the cockpit. This is not a gradual failure where the engine slowly loses power over minutes, giving the crew time to diagnose and respond methodically. This is instantaneous catastrophic destruction. One moment you have two good engines producing climb thrust. The next moment you have one good engine and one destroyed engine and a cockpit full of warnings, and a sudden yaw as asymmetric thrust tries to turn the aircraft. Based on physical evidence from the crash site, this appears to be exactly what happened to the right-hand engine, the number 2 engine, on the Biffle flight. Post-crash photographs examined by multiple aviation analysts show clear and unmistakable foreign object damage to the fan blades of the right engine. Blades are bent at unnatural angles. Some blades appear to be completely missing. The inlet cowling shows damage. This is the signature of FOD, foreign object damage, and it tells us that something substantial, something with real mass, entered that engine while it was running at high power. We also know from those same photographs that the right-hand forward baggage compartment door is missing from the wreckage. Now, the NTSB has not yet officially stated whether that door separated in flight or was torn off during the crash impact sequence. But when you put these two pieces of evidence together, a missing right baggage door and a destroyed right engine with clear FOD, the most likely explanation becomes apparent. That baggage door opened in flight, items from the baggage compartment were sucked out by the airflow and pressure differential, and at least some of those items were ingested directly into the right engine, destroying it. This scenario has documented precedent. It has happened before on Citation aircraft multiple times. In 2024, a Citation 2 departing Barranquilla, Colombia, experienced exactly this sequence. Right baggage door opened after takeoff, items ingested into right. Engine destroyed, crew declared emergency and returned to land safely on the left engine. Everyone survived. In 2007, another Citation experienced a baggage door opening after takeoff. The crew became distracted by the chaos and noise. They lost control of the aircraft. It stalled at low altitude and crashed. Everyone died. So we have precedents with two completely opposite outcomes. Same mechanical failure, same initiating event, but one crew survived and one didn't. This tells us something critically important. The mechanical failure itself, the engine destruction, was survivable. It should have been survivable. The aircraft was fully capable of flying on one engine. The crew should have been able to manage the emergency and return safely. So why didn't they? What was different about the Biffle flight that turned a survivable mechanical failure into a fatal accident? To answer that, we need to understand what's supposed to happen when a mechanical failure like this occurs and what actually happened on this flight. Let's start with the design philosophy. The Citation 2 is certificated under FAA regulations that require demonstrated single-engine capability. The manufacturer had to prove during the certification process that the aircraft can safely take off, climb, maneuver, and land with one engine completely inoperative. There are specific performance requirements: minimum single-engine climb gradient, minimum single-engine service ceiling, maximum demonstrated single-engine landing distance. All of this is tested and verified before the aircraft can be certified for sale. Additionally, pilots who want to fly the Citation must obtain a type rating, a specific certification that requires training in that exact aircraft type. Part of that training, a mandatory part, is engine failure procedures. Pilots must demonstrate in a simulator or in the actual aircraft that they can handle an engine failure during takeoff. The most critical phase, they must show they can identify the failed engine, secure it properly, maintain control of the aircraft, and safely return to land. If they can't demonstrate this competency, they don't get the type rating. So in theory, when an engine fails on a Citation, the pilot should be thoroughly trained and ready. They should recognize the failure immediately from the yaw, the warnings, the instrument indications. They should execute the memory items, the immediate actions that must be done without reference to a checklist. They should identify which engine has failed, verify it's actually failed, and begin securing it. Then they should pull out the written checklist and methodically work through the complete engine shutdown and securing procedure while the other pilot flies the aircraft and maintains a safe flight path. This is called crew resource management. and it's fundamental to how multi-pilot aircraft are designed to operate. The pilot flying focuses on flying, maintaining control, maintaining airspeed above minimum control speed, maintaining a safe altitude above terrain, maintaining awareness of position relative to the airport. The pilot not flying focuses on systems management, running checklists, making radio calls, setting up approaches, managing the emergency. Two pilots, two separate but complementary roles working together as a crew. But this only works if you actually have two qualified, trained, competent pilots. And this is where we start to uncover the vulnerabilities that turned a survivable mechanical failure into a fatal one. We know there were 3 people on board the aircraft. All 3 were certificated pilots, meaning they all held FAA pilot licenses. But only one of them held a citation type rating. Only one was actually qualified to act as pilot in command of a citation. That person was Dennis Dutton. Dennis Dutton was 67 years old, recently retired from Delta Airlines, where he had served as a captain on various aircraft types over a career spanning more than 3 decades. By every available measure, Dennis was a consummate professional, highly experienced, highly trained, current and proficient, the kind of pilot you would want in the left seat if an emergency occurred. Under normal circumstances, with a properly qualified and competent co-pilot, Dennis should have been entirely capable of handling an engine failure and bringing the aircraft back safely. But we don't know who was in that right seat, and that question is absolutely central to understanding why this mechanical failure ended everything. The other 2 people on board were Dennis's son, Jack, age 21, a college junior studying professional flight at Auburn University, and Greg Biffle, age 54, NASCAR champion and owner of the aircraft. Let's examine each of their qualifications and what they could or couldn't bring to an emergency situation. Jack Dutton held a private pilot certificate for single-engine land aircraft. He had recently earned his instrument rating, an important milestone in pilot training that qualifies you to fly in clouds and reduced visibility using only instruments. These are significant accomplishments, and they indicate Jack was serious about aviation and working toward a professional career. But there's one critical thing Jack did not have. He did not hold a multi-engine rating. According to FAA records, he was not qualified to fly any multi-engine aircraft, not even a basic piston twin like a Piper Seminole, let alone a sophisticated twin-engine jet. This matters for several reasons. First, multi-engine operations are fundamentally different from single-engine operations. When you lose an engine on a single-engine aircraft, you're gliding, looking for a place to land. When you lose an engine on a multi-engine aircraft, you have asymmetric thrust, which creates yaw and roll that must be actively countered with rudder and aileron. You have to identify which engine failed, secure it properly, reconfigure systems, and fly the aircraft with degraded performance. None of this is intuitive. All of it requires specific training. Second, without a multi-engine rating, Jack would not have been legally qualified to serve as a required crew member on the citation under any circumstances. Now, under Part 91 regulations governing private operations, passengers are allowed to sit in the cockpit, they're allowed to occupy the right seat. They can even manipulate controls under the supervision of the pilot in command, but they cannot serve as a required crew member. They cannot log the time as flight time. And most importantly, they cannot provide the crew resource management, the system backup that a properly qualified second-in-command provides. If Jack was in the right seat when the engine failed, Dennis would have been essentially alone. Jack could perhaps have read checklists aloud if directed. He could have called out altitudes and airspeeds, but he couldn't have run the engine shutdown procedure independently. He couldn't have managed aircraft systems. He couldn't have set up approaches or made informed decisions about emergency options. He would have been, from a crew resource management perspective, a passenger, not a pilot. Now let's consider Greg Biffle. Greg did hold a multi-engine rating according to public records. Under Part 91 regulations, he could have legally served as second-in-command if he met certain familiarization requirements. These requirements include things like knowledge of aircraft systems, knowledge of emergency procedures, familiarity with normal and abnormal checklists, and completion of a certain number of takeoffs and landings in the aircraft. The requirements are not as stringent as they would be for a type-rated pilot or for Part 135 operations, but they do exist. The question is whether Greg had actually met those requirements, and more importantly, whether he had achieved true proficiency or just technical compliance. There's a huge difference. You can technically meet familiarization requirements by sitting through some ground training and making a few takeoffs and landings, but that doesn't make you proficient. That doesn't mean you can actually function effectively as a crew member during a real emergency when stress is high, time is short, and every action matters. Greg Biffle was an extraordinarily accomplished race car driver. He understood high-speed operations, risk management, split-second decision-making. He was clearly passionate about aviation and had invested significantly in his training. But racing skill doesn't automatically translate to aviation proficiency, especially in a complex aircraft like a jet. The question that matters for this accident is whether Greg, if he was in the right seat, was truly capable of serving as an effective second in command during an engine failure emergency. Could he have run the checklist quickly and accurately? Could he have managed systems while Dennis flew? Could he have made informed decisions about emergency procedures? We don't know the answers yet. The NTSB knows because this aircraft had a cockpit voice recorder installed. That recorder captured everything that was said, every action that was taken, every warning that sounded. The NTSB knows exactly who was sitting where and exactly what role each person played during the emergency. But they haven't publicly disclosed that information yet, and they won't until the preliminary report is released. What we can say is this: if the person in the right seat, whether it was Jack or Greg, was not truly capable of functioning as an effective crew member during the emergency, then Dennis was flying alone. He was trying to do two jobs simultaneously: fly the aircraft with a failed engine and asymmetric thrust, manage all the systems and run all the checklists, make all the decisions about where to go and how to configure the aircraft, maintain situational awareness about position, altitude, terrain, weather, all of it alone in a high-stress emergency at low altitude with minimal time. Even for a pilot as experienced as Dennis Dutton, that's an overwhelming workload. And this brings us to the second major vulnerability, the lack of adequate margins. In aviation, margins are everything. Margins are the buffer between normal operations and disaster. Altitude is a margin, time is a margin, fuel is a margin, weather visibility is a margin, crew capability is a margin, equipment redundancy is a margin. When you have adequate margins, you can absorb failures, mistakes, and unexpected events without catastrophic consequences. When margins are thin or absent, any failure or any mistake can be fatal. Let's examine what margins existed or didn't exist on the Biffle flight. Start with altitude. The flight departed Statesville Regional Airport, a small public airport in rolling terrain about 30 miles north of Charlotte. Weather that morning included cloud ceilings at approximately 1,200 feet broken. If the crew was operating under visual flight rules, which appears likely since there's no evidence they were in contact with air traffic control, they would have needed to remain clear of clouds. 1,200-foot ceilings mean you're probably flying at or below 2,000 feet to stay legal VFR. And indeed, the limited ADS-B tracking data we have shows the aircraft climbed to approximately 2,000 feet, then leveled off. 2,000 feet. That's not much altitude. That's maybe 2 to 3 minutes of flight time before you must be on a runway if you lose an engine. Compare that to a flight departing from a major airport in good weather that might climb to 5 or 10,000 feet before an engine failure occurs. At 10,000 feet, you have 15 to 20 minutes to work the problem. At 2,000 feet, you have maybe 3 minutes. Next, consider weather. Ceilings 1,200 broken, visibility 5 miles in light drizzle. These are legal VFR minimums, but their marginal visibility is reduced. Cloud bases are low. The visual references are poor. If you're trying to maneuver back to an airport and set up an approach in these conditions, you don't have the clear visual references that would allow you to judge altitude and distance accurately. It's very easy to misjudge your height above ground, very easy to end up too low on approach, very easy to become spatially disoriented, especially if you're also dealing with the stress and workload of an emergency. Then consider time. From takeoff to impact was approximately 10 minutes. That's how much time the crew had to recognize the emergency, diagnose what was happening, make decisions about where to go, configure the aircraft, run checklists, maneuver back to the airport, set up an approach, and land. 10 minutes. In airline operations with two experienced crews working together, with ATC support, 10 minutes might be adequate. For one pilot possibly flying alone in marginal weather at low altitude, 10 minutes is barely enough to execute the basics. Next, consider equipment. The baggage door that apparently opened had no cockpit monitoring, no warning light, no sensor, nothing to tell the crew it wasn't secured. This is a single point failure mode entirely dependent on human memory and attention. If someone forgets to check it or thinks it's latched when it isn't, there's no backup. This is poor design from a human factor standpoint, and it's a missing margin. A simple sensor and warning light technology that's existed for decades would have prevented this entire sequence. But it wasn't there. Consider crew capability as a margin. If the right seat was occupied by someone not truly capable of serving as an effective second in command during an emergency, that margin was absent. Dennis was flying without the backup that multi-crew aircraft are designed to have. Finally, consider decision-making under stress. Even experienced pilots can make mistakes when faced with sudden emergencies, especially when workload is high and time is short. Having a competent second pilot provides a check on decision-making, two sets of eyes, two perspectives, two chances to catch an error. Without that, errors go uncaught. When you add all of this up, what you see is an operation with very thin margins or no margins at all. Low altitude, minimal time, marginal weather, reduced visibility, no warning system for the baggage door, possibly inadequate crew capability with one pilot flying alone. Any one of these by itself might not be fatal, but when they all exist simultaneously, when multiple margins are absent at the same time, the system has no ability to absorb a failure. And that's why this one mechanical failure ended everything. Not because the failure itself was catastrophic, but because the system it occurred in had no margins left to absorb it. The engine destruction should have been survivable. The aircraft could fly on one engine. The pilot was qualified and experienced. But the margins that should have made it survivable weren't there. The altitude wasn't sufficient. The time wasn't sufficient. The weather didn't provide sufficient visual reference. The crew capability may not have been sufficient. And when you're operating with zero margins, any failure, even one you're designed and trained to handle, can end everything. Let's walk through what likely happened in those final minutes. The aircraft departs runway 10 and begins climbing. Everything appears normal. Both engines are running well. The crew is probably relaxed, thinking about the flight ahead, maybe talking about arrival plans. Then probably somewhere between 1,000 and 2,000 feet, the baggage door opens. Maybe it wasn't latched at all. Maybe it was partially latched, but not fully secured. Maybe it vibrated loose. However it happened, once the aircraft is in the air and accelerating, the pressure differential and airflow are tremendous. The door is blown open violently. Items in the baggage compartment, suitcases, bags, loose articles, are immediately sucked out. Some of those items, because of the location of the baggage door directly ahead of the engine intake, go straight into the right engine. The engine ingests something solid, something it can't process. Fan blades strike it at high speed. Blades shatter. The engine destroys itself in 2 to 3 seconds. Suddenly the cockpit is full of warnings, master warning lights, engine fire warnings possibly, aural alarms. The aircraft yaws to the right as the right engine loses thrust while the left engine continues producing power. Dennis Dutton, experienced professional that he is, immediately applies left rudder to counteract the yaw. He verifies which engine has failed by looking at the instruments. He starts the memory items, pulling back the throttle on the failed engine. But he's also dealing with chaos. If the baggage doors open, there's tremendous wind noise, potentially items flying around inside the cabin. There's uncertainty about what's actually happening. Is it just an engine failure, or is there more wrong? He has to make immediate decisions. Continue climbing or level off, turn back immediately or climb away first. Where's the airport? What's the runway alignment? What's the wind? If there's a competent co-pilot in the right seat, that person is already pulling out the engine failure checklist, already starting to run through the shutdown procedure, already thinking about approach setup and landing configuration. But if there isn't, if the person in the right seat doesn't know what to do or is frozen by stress and uncertainty, then Dennis has to do all of it himself while hand flying an aircraft with asymmetric thrust in marginal weather at low altitude. He makes a decision, probably the right decision, to return immediately. He's low, probably only at 2,000 feet. He's close to the airport. It makes sense to get back on the ground as quickly as possible rather than climbing away. He begins a turn. He's probably trying to set up for runway 28, the opposite direction from departure. He levels off, starts descending, trying to line up with the runway, but now he's in a critical situation. He's low, probably 1,500 feet or less. He's maneuvering with asymmetric thrust. He's in marginal weather with reduced visibility. He's trying to judge his position and altitude relative to the airport without clear visual references. He's trying to configure the aircraft get the landing gear down, maybe extend some flaps. He's trying to run checklist or at least the critical items. He's trying to maintain airspeed above minimum control speed while also maintaining enough altitude to reach the runway. It's an enormous workload. And somewhere in those final moments, something goes wrong. Maybe he misjudges his altitude and descends too early. Maybe he slows too much trying to stretch the glide and gets dangerously close to stall speed. Maybe he becomes spatially disoriented in the reduced visibility. Maybe he's simply too low and too far out to make the runway with single engine performance. The final ADS-B data point shows the aircraft low and apparently lined up with runway 28. Then nothing. 30 seconds later, the aircraft impacts terrain 1,800 feet short of the runway threshold. 1,800 feet. Less than a third of a mile. They were so close. If they'd had just a few hundred more feet of altitude, if they'd been just a little faster, if they'd started the descent just a little later, they would have made it. But they didn't. In aviation, close doesn't count. Either you make the runway or you don't. And this is where we come to the hard truth. This accident was likely not about what Dennis Dutton did wrong. It was probably about an impossible situation created by absent margins. You cannot successfully manage a high workload emergency alone when you should have crew assistance. You cannot safely return from an engine failure at 2,000 feet in marginal weather when you should have more altitude. You cannot make precise judgments about altitude and distance without clear visual references when you should have better weather. You cannot overcome multiple simultaneous deficiencies in the system when you should have adequate margins. The mechanical failure, the engine destruction was the trigger, but the absent margins were the reason that trigger proved fatal. If there had been a properly qualified and capable co-pilot in the right seat, the workload would have been shared. If there had been 5,000 feet of altitude instead of 2,000, there would have been time to work the problem properly. If the weather had been clear, visual references would have been available. If there had been a warning system for the baggage door, maybe it would have been discovered before flight or at least immediately upon opening. But none of those margins existed. And when you operate without margins, you're gambling that nothing will go wrong. Most of the time, that gamble pays off. Flights are routine, nothing fails. You land safely and never think about how close you might have been to disaster if something had gone wrong. But when you lose that gamble, when something does go wrong while you're operating with no margins, the results are often fatal. This is the lesson that transcends this specific accident. This is the lesson that applies to everyone who operates aircraft or any complex system in high-risk environments. Margins are not luxuries. They're not optional nice-to-haves. They're the difference between a survivable emergency and a fatal accident. Every margin you give up, every buffer you reduce, every safety factor you accept at minimum rather than building it higher, you're making a bet that nothing will go wrong. The regulations set minimums, but minimums are not targets. You're allowed to fly VFR in 1,200-foot ceilings, but that doesn't mean you should. You're allowed to have a minimally qualified second-in-command who technically meets requirements, but that doesn't mean they'll be useful in an emergency. You're allowed to accept single-point failure modes like unmonitored baggage doors on older aircraft, but that doesn't mean you're safe. Professional operations, airlines, and high-end corporate flight departments understand this implicitly. They build margins into everything. Weather minimums higher than regulatory minimums, crew qualifications far exceeding regulatory minimums, maintenance standards stricter than required, fuel reserves larger than required, multiple layers of safety built into every decision. And when something goes wrong, when a mechanical failure occurs, those margins absorb it, the emergency is handled, the aircraft lands safely, everyone goes home. Part 91 operations, private flying often operates much closer to minimums, tighter margins, more acceptance of minimum standards, more tolerance for single points of failure. And most of the time it works fine because serious mechanical failures are rare. But when that rare failure occurs, when the engine blows at the worst possible moment, the absence of margins turns a survivable emergency into a tragedy. That's how one mechanical failure ended everything for Greg Biffle, Dennis Dutton, and Jack Dutton, not because the failure itself was unsurvivable, but because the system they were operating in had no margins left to absorb it. The preliminary report will be released soon. We'll learn more specifics.